Empirical and molecular formulas overview. Empirical and molecular formulas are fundamental concepts in chemistry used to represent the composition of chemical compounds. An empirical formula shows the simplest whole number ratio of atoms in a compound, while a molecular formula provides the actual number of each type of atom present in a molecule. Elemental analysis, a method to determine the percent composition of elements in a compound, often involves techniques like combustion analysis to determine the amounts of elements like carbon and hydrogen. Calculating empirical formula involves determining the simplest whole number ratio of atoms in a compound. Steps: convert percent composition to grams, convert grams to moles, and find the smallest whole number ratio of moles. Molecular weight, the mass of a molecule, calculated by summing the atomic weights of all atoms in the molecule. Essential for determining the molecular formula from the empirical formula. Empirical formula relation, the molecular formula is a whole number multiple of the empirical formula. Molecular formula equals n empirical formula, where n is a whole number. Combustion analysis. A common experimental technique used to determine the empirical formula of a compound containing carbon, hydrogen, and sometimes oxygen. The compound is burned in excess oxygen, and the masses of CO2 and H2O produced are measured. Ascorbic acid example. Illustrates the application of empirical and molecular formula calculations using ascorbic acid, vitamin C, as an example. Shows how to determine the empirical and molecular formulas based on percent composition or combustion analysis data. Empirical formula determination, the process of finding the simplest whole number ratio of atoms in a compound. Key steps include converting mass or percent composition to moles and determining the mole ratio. Unknown compound analysis. Applying the concepts of empirical and molecular formulas to identify an unknown compound. Involves using experimental data, for example, combustion analysis, elemental analysis, and molar mass determination, to determine the compound's formula. Dalton's atomic theory overview. Dalton's atomic theory, proposed in the early 19th century, laid the foundation for modern chemistry by describing matter in terms of atoms and their interactions. It proposed that all matter is composed of indivisible atoms, with specific properties determining chemical behavior. Atoms are smallest particles. Matter is composed of extremely small particles called atoms. Atoms are the fundamental building blocks of elements. Elements and types of atoms. All atoms of a given element are identical in mass and properties. Atoms of different elements have different masses and properties. Atomic properties. Atoms are the smallest unit of an element that can participate in a chemical reaction. Compounds and ratios of elements. Compounds are formed when atoms of different elements combine. A given compound always has the same relative numbers and types of atoms. Law of definite proportions. Atoms combine in simple whole number ratios to form compounds. Conservation of atoms. In chemical reactions, atoms are neither created nor destroyed, they are simply rearranged. Laws of proportions overview. The laws of proportions are a set of fundamental principles in chemistry that describe how elements combine to form compounds. These laws help to understand the quantitative relationships between elements in chemical reactions. Law of multiple proportions. When two elements combine to form more than one compound, the masses of one element that combine with the fixed mass of the other element are in a ratio of small whole numbers. Compound formation. The laws of proportions explain how different elements combine to form chemical compounds with definite compositions. These laws are foundational to understanding chemical formulas and stoichiometry. Solutions overview. Solutions are homogeneous mixtures composed of a solute dissolved in a solvent. Properties of solutions. Homogeneous mixtures. Solute is dissolved in the solvent. Concentration of solutions describes the amount of solute in a given amount of solution or solvent. Various methods exist to express concentration quantitatively. Molarity, defined as the number of moles of solute per liter of solution, mol/L. Formula, molarity, M equals moles of solute, liters of solution. Molality, defined as the number of moles of solute per kilogram of solvent, mol/Kg. Formula, molality, M equals moles of solute, kilograms of solvent. Parts per million, ppm, expresses the concentration of solute in very dilute solutions. Represents the mass of solute per million parts of the solution. Formula, ppm equals mass of solute, mass of solution, 1 million. Percent weight, expresses the concentration as the mass of solute per 100 grams of solution. Also known as percent mass or weight/weight percent, percent WW. Formula, percent weight equals mass of solute, mass of solution, 100%. Chemical reactions, bond formation and breaking. Chemical reactions involve the breaking of existing chemical bonds within reactant molecules. New chemical bonds are formed to create product molecules. Types of chemical reactions, synthesis reactions, two or more reactants combine to form a single, more complex product. General form, A plus B at decomposition reactions, a single compound breaks down into two or more simpler substances. General form, A plus B single replacement reactions, a more reactive element replaces a less reactive element in a compound. General form, A plus BC AC plus B double replacement reactions. The positive and negative ions of two different compounds switch places, forming two new compounds. General form, A plus CB AD plus CB combustion reactions. A substance rapidly reacts with oxygen, often producing heat and light. Typically involves a fuel reacting with oxygen, for example, burning of hydrocarbons. Neutralization reactions, a reaction between an acid and a base. Typically results in the formation of salt and water. Formula mass and composition. Overview. Formula mass is the sum of the atomic masses of all atoms in a chemical formula, and it's essential for understanding the composition of substances. This concept is fundamental in determining the molar mass and the mass percentages of elements in a compound. Atomic masses. Definition. The mass of an atom, typically expressed in atomic mass units, AMU. Relevance. Used to calculate the formula mass of a substance. Moles. Definition. A unit of measurement for the amount of a substance, 6.022 by 10 squared cubed entities. Relevance. Used to relate the mass of a substance to the number of molecules or formula units. Calcium phosphate. Example. A specific ionic compound, Ca3PO42. Application. Illustrates how to calculate formula mass for ionic compounds. Elemental makeup. Definition. The types and amounts of elements present in a compound. Relevance. Directly related to the molecular formula and mass percentages. Mass percentage. Definition. The mass of an element in a compound expressed as a percentage of the total mass of the compound. Calculation. Mass of element. Formula mass of compound. X 100%. Importance. Used to determine the purity and composition of a substance. Molecular formula, definition, a formula that indicates the actual number of each element present in a molecule. Relevance, essential for calculating the formula mass and determining mass percentages. Chemical reactions. Overview, chemical reactions involve the rearrangement of atoms and molecules, following specific principles like the conservation of matter. These reactions encompass various types, including combustion, redox, and those occurring in solution or involving electrochemical and nuclear processes. Law of conservation of matter. Matter is neither created nor destroyed in a chemical reaction, the total mass remains constant. Involved in a chemical reaction. Atom conservation, the number of atoms of each element remains the same throughout a chemical reaction. Coefficients. Numbers placed in front of chemical formulas in balanced equations to indicate the relative number of molecules or moles of each reactant and product. Combustion reactions. Chemical reactions that involve rapid reaction between a substance with an oxidant, usually oxygen, to produce heat and light. Redox reactions. Reactions involving the transfer of electrons between chemical species, including oxidation and reduction processes. Solution phase chemistry, chemical reactions that occur in a solution, where reactants are dissolved in a solvent. Solution phase reactions, specific reactions that take place within a solution, influenced by factors like concentration and solubility. Nuclear reactions. Reactions that involve changes in the nuclei of atoms, leading to transformations of elements and the release of energy. Electrolytes overview. Electrolytes are substances that dissociate into ions when dissolved in a solvent, making the solution capable of conducting electricity. They are crucial for various biological and chemical processes. Strong electrolytes. Define strong electrolytes. What are some examples of strong electrolytes? How do strong electrolytes behave in solution? Weak electrolytes. Define weak electrolytes. What are some examples of weak electrolytes? How do weak electrolytes behave in solution compared to strong electrolytes? Electrical conductivity. Explain how electrolytes enable electrical conductivity in solutions. What factors affect the electrical conductivity of an electrolyte solution? How does the concentration of an electrolyte impact its conductivity? Aqueous solutions. What is an aqueous solution? How do electrolytes behave in aqueous solutions? Why is water a common solvent for electrolytes? Combustion analysis overview. Combustion analysis is a technique used to determine the empirical and molecular formulas of a compound by burning a sample and analyzing the products formed. This method is especially useful for determining the composition of organic compounds containing carbon, hydrogen, and sometimes oxygen. Combustion reaction involves burning a compound in the presence of excess oxygen. Carbon in the compound is converted to carbon dioxide, CO2. Hydrogen in the compound is converted to water, H2O. The amount of CO2 and H2O produced is measured to determine the amounts of carbon and hydrogen in the original compound. Empirical formula determination. Use the masses of CO2 and H2O produced to calculate the masses of carbon and hydrogen in the original compound. Convert the masses of carbon and hydrogen to moles. Determine the mole ratio of the elements. The empirical formula represents the simplest whole number ratio of the elements in the compound. Molecular formula determination requires the empirical formula and the molar mass of the compound. Calculate the empirical formula mass. Divide the molar mass of the compound by the empirical formula mass to find the whole number multiplier. Multiply the subscripts in the empirical formula by this multiplier to obtain the molecular formula. Solutions and mixtures. Pure substance, a substance with a constant composition and distinct properties. Cannot be separated into simpler substances by physical means. Examples include elements and compounds. Constant composition, a mixture or substance that has the same ratio of components throughout. Pure substances have a constant composition. Stoichiometry overview. Stoichiometry is the calculation of reactants and products in chemical reactions. It is based on the law of conservation of mass and uses balanced chemical equations to determine the quantitative relationships between substances involved in a reaction. Balancing equations, ensuring the number of atoms for each element is equal on both sides of the equation. Involves adjusting coefficients in front of chemical formulas. Essential for accurate stoichiometric calculations. Moles. 1 mole contains 6.022 by 10 squared cubed particles, Avogadro's number. Molar ratio, the ratio of the amounts of moles of any two substances involved in a chemical reaction. Derived from the coefficients in the balanced chemical equation. Used to convert between the amount of one substance and the amount of another substance in a reaction. Limiting reagent, the reactant that is completely consumed in a chemical reaction. Determines the maximum amount of product that can be formed. Identified by comparing the mole ratio of reactants to the stoichiometric ratio from the balanced equation. Theoretical yield, the maximum amount of product that can be produced from a given amount of reactants. Calculated based on the balanced equation and the amount of the limiting reactant. Percent yield, a measure of the efficiency of a chemical reaction. Calculated as actual yield, theoretical yield, x 100%. Actual yield is the amount of product actually obtained in an experiment. Reaction equations. Molecular equations represent the complete chemical formulas of reactants and products. Show the reactants and products as if they exist as intact molecules. Complete ionic equations show all soluble ionic compounds dissociated into their respective ions. Helps to visualize the ions present in the solution during the reaction. Balanced chemical equations, equations where the number of atoms for each element is the same on both sides of the equation. Follows the law of conservation of mass. Net ionic equations focus on the ions that participate in the reaction, excluding spectator ions. Provides a simplified view of the actual chemical change occurring. Balancing elements. Ensuring the same number of atoms of each element appear on both the reactant and product sides of the equation. Achieved by adjusting coefficients in front of the chemical formulas. Balancing oxygen and hydrogen, often balanced last, after all other elements. Water, H2O, is commonly used to balance oxygen and hydrogen atoms in the equation. Precipitation reactions overview. Precipitation reactions involve the formation of an insoluble solid, precipitate, when two or more soluble ionic compounds are mixed in solution. Soluble versus insoluble compounds. Soluble compounds dissolve in water and dissociate into ions. Insoluble compounds, or sparingly soluble, do not dissolve and form a solid precipitate. The distinction between soluble and insoluble is based on the solubility rules. Spectator ions, ions that are present in the reaction but do not participate in the formation of the precipitate. They remain dissolved in the solution throughout the reaction. Net ionic equations, chemical equations that show only the ions that directly participate in the precipitation reaction. Spectator ions are excluded from net ionic equations, focusing on the formation of the precipitate. Solution chemistry. Overview. Solution chemistry is the study of the physical and chemical properties of solutions, which are homogeneous mixtures composed of a solute dissolved in a solvent. It encompasses understanding the interactions between solutes and solvents, the processes of dissolution, and the behavior of substances in solutions, including ionization and precipitation. Solutions, homogeneous mixtures. Contain a solute and a solvent. Dissolution, the process where a solute disperses uniformly in a solvent. Affected by solute-solvent interactions. Solute and solvent interactions, forces of attraction between solute and solvent particles. Influence the solubility of a solute. Methanol dissolution. Methanol is a polar molecule that dissolves in water. Involves the breaking of hydrogen bonds. Electrolytes and non-electrolytes. Electrolytes, substances that produce ions in solution and conduct electricity. Non-electrolytes, substances that do not produce ions and do not conduct electricity. Conductivity in solutions, the ability of a solution to conduct electricity. Depends on the presence and concentration of ions. Precipitation, the formation of a solid, precipitate from a solution. Occurs when the concentration of ions exceeds the solubility limit. Ionization, the process where a molecule gains or loses electrons to form ions. Common in acids and bases. Dissociation, the separation of ions from an ionic compound when dissolved in a solvent. Example, NaCl dissociating into Na+ and Cl ions in water. Polar molecules, molecules with an uneven distribution of charge. Have a positive and a negative end. Water and methanol are polar molecules. Hydrogen bonds, a strong type of dipole-dipole interaction. Occurs between a hydrogen atom bonded to a highly electronegative atom, like oxygen or nitrogen, and another electronegative atom. Important in the properties of water and other solvents. Chemical reactions. Overview. Chemical reactions involve the rearrangement of atoms and molecules, transforming reactants into products. They are governed by the law of conservation of matter and can be classified into various types based on the nature of the chemical changes involved. Law of conservation of matter states that matter cannot be created or destroyed in a chemical reaction. The total mass of the reactants must equal the total mass of the products. Reaction types. Combustion reactions, reactions that involve the rapid reaction between a substance with an oxidant, usually oxygen, to produce heat and light. Often involve hydrocarbons reacting with oxygen to produce carbon dioxide and water. Precipitation reactions, reactions where an insoluble solid, precipitate, forms from the mixing of two solutions. Acid/base reactions, reactions that involve the transfer of protons, H+, between an acid and a base. Redox reactions, reactions that involve the transfer of electrons between reactants. Nuclear reactions, reactions that involve changes in the nucleus of an atom. Synthesis reactions, reactions where two or more reactants combine to form a single product. Generally represented as A plus B AB. Decomposition reactions, reactions where a single reactant breaks down into two or more products. Generally represented as AB A plus B. Metathesis. Reactions, a type of double displacement reaction where the cations and anions of two reactants switch places. Single replacement reactions, a reaction where a more reactive element replaces a less reactive element in a compound. Generally represented as A plus BC AC plus B. Double replacement reactions, reactions where the cations of two reactants switch places, forming two new compounds. Generally represented as A plus CD AD plus CB. Stoichiometry overview. Stoichiometry is a branch of chemistry that involves using relationships between reactants and products in a chemical reaction to determine desired quantitative data. It is based on the law of conservation of mass and involves calculations related to the amounts of substances involved in chemical reactions. Mole concept, definition and significance. The mole is a unit of measurement for the amount of substance. Understanding the mole is fundamental to stoichiometry. Avogadro's number relates the mole to the number of particles, atoms, molecules, ions. Molar mass, definition, the mass of 1 mole of a substance, gram/mole. Calculating molar mass, determining molar mass from the periodic table. Mole ratios, definition, the ratio of the amounts of moles of reactants and products in a balanced chemical equation. Using mole ratios, converting between moles of reactants and products. Mass to mole conversions, conversion factors, utilizing molar mass to convert between mass and moles. Applications, calculating the number of moles from a given mass and vice versa. Amount of substance, definition, this refers to the quantity of a substance, typically measured in moles. Mole calculations, calculating moles of reactants and products given mass, volume, or concentration. Mass conversion, converting between the mass of reactants and products using stoichiometry. Molecular formula, definition, a formula that gives the exact number of each type of atom in a molecule. Empirical formula, definition, the simplest whole number ratio of atoms in a compound. Determining empirical formula, calculating from percent composition or mass data. Molarity, definition, the concentration of a solution expressed as moles of solute per liter of solution. Calculations, determining molarity and using molarity in stoichiometric calculations. Molality, definition, the concentration of a solution expressed as moles of solute per kilogram of solvent. Parts per million, definition, a way to express the concentration of very dilute solutions. Percent weight, definition, expressing the concentration of a solution as a percentage by weight. Limiting reactant. Definition, the reactant that is completely consumed in a chemical reaction, which determines the amount of product formed. Excess reagents, definition, reactants present in amounts greater than what is needed to react with the limiting reactant. Identifying limiting reagents, steps, determining the limiting reactant from the amounts of reactants provided. Calculations involving limiting reagents, determining the amount of product formed when a limiting reactant is present. Calculating the amount of excess reactant remaining after the reaction. Theoretical yield. Definition, the maximum amount of product that can be formed from a given amount of reactants, assuming the reaction goes to completion. Actual yield, definition, the amount of product actually obtained from a chemical reaction. Product yield calculation, calculating the amount of product formed in a reaction using stoichiometric principles. Percent yield, definition, the ratio of the actual yield to the theoretical yield, expressed as a percentage. Calculating percent yield, formula, actual yield, theoretical yield, x 100%. Precipitation reactions overview. Precipitation reactions involve the formation of an insoluble solid, precipitate, when two or more soluble ionic compounds are mixed in solution. These reactions are governed by solubility rules that determine which compounds will precipitate out of solution. Solubility rules, rules used to predict whether an ionic compound is soluble or insoluble in water. These rules are based on empirical observations and guide the prediction of precipitate formation. Soluble versus insoluble compounds. Soluble compounds dissolve in water and dissociate into ions. Insoluble compounds do not dissolve in water, they form a precipitate. Formula equation, molecular equation, represents the balanced chemical equation using the complete formulas of all reactants and products, including any precipitates. All compounds are written in their molecular form, even if they are ionic and dissociate in solution. Complete ionic equation shows all soluble ionic compounds dissociated into their respective ions. Precipitates are shown as solids. Net ionic equation shows only the ions directly involved in the precipitation reaction. Spectator ions, ions that do not participate in the reaction, are omitted. Stoichiometry in solution overview. Stoichiometry in solution involves applying stoichiometric principles to reactions occurring in liquid solutions. This includes determining reactant amounts, predicting product formation, and calculating concentrations and quantities. Calculating moles of reactants determine the molarity and volume of the solution. Use the formula moles equals molarity x volume in liters. Calculating moles of product. Use the balanced chemical equation to find the mole ratio between reactants and products. Use the moles of reactants to calculate the moles of product formed. Limiting reactants. Identify the limiting reactant by comparing the mole ratios of reactants to the stoichiometric ratios in the balanced equation. The limiting reactant determines the maximum amount of product that can be formed. Precipitate formation. Identify the formation of a precipitate based on solubility rules. Write the balanced chemical equation, including the states of matter. Mass calculation of precipitates. Calculate the moles of the precipitate formed using stoichiometry. Convert moles to grams using the molar mass of the precipitate. Converting to grams or volume. Convert moles of reactants or products to grams using molar mass. Convert moles or grams to volume using molarity and density, respectively. Redox reactions overview. Redox reactions, or oxidation-reduction reactions, involve the transfer of electrons between chemical species. These reactions are fundamental to various processes, including corrosion, combustion, and cellular respiration. Oxidation, loss of electrons, defined as the loss of electrons by a substance. The substance that undergoes oxidation is the reducing agent. Example, a metal atom losing electrons to form a positive ion. Reduction, gain of electrons, defined as the gain of electrons by a substance. The substance that undergoes reduction is the oxidizing agent. Example, a non-metal atom gaining electrons to form a negative ion. Assigning oxidation states. Oxidation states, also known as oxidation numbers, are assigned to atoms in a molecule or ion to track electron transfer. Rules are followed to determine the oxidation state of an atom in a compound. Oxidation states help identify which species are oxidized or reduced in a redox reaction. Balancing redox reactions. Redox reactions must be balanced to satisfy the law of conservation of mass and charge. Common methods include the half reaction method and the oxidation number method. Balancing ensures that the number of electrons lost equals the number of electrons gained. Oxidizing agent, a substance that causes oxidation in another substance. It itself is reduced in the process, gains electrons. Examples include oxygen, halogens, and certain metal ions. Reducing agent, a substance that causes reduction in another substance. It itself is oxidized in the process, loses electrons. Examples include alkali metals, some nonmetals, and certain reducing agents used in organic chemistry. Acid-base reactions. Overview. Acid-base reactions involve the transfer of protons, H+, or the acceptance/donation of electron pairs, leading to changes in pH. These reactions are fundamental in chemistry and are categorized based on different definitions of acids and bases. Species present before reaction. Identify reactants involved in acid-base reactions before they interact. Predict the initial chemical species, including acids, bases, and potential solvents. Net ionic equation. Write balanced equations for acid-base reactions, showing only the species involved in the reaction. Cancel out spectator ions. Acid-base reactions. Understand the general concept of acids reacting with bases. Recognize and classify different types of acid-base reactions based on the definitions of acids and bases. Brunstad-Lowry acids and bases. Define acids as proton donors and bases as proton acceptors. Identify conjugate acid-base pairs in reactions. Lewis acids and bases. Define acids as electron pair acceptors and bases as electron pair donors. Recognize reactions involving Lewis acids and bases. Strong versus weak acids. Differentiate between strong acids, completely dissociate in water, and weak acids, partially dissociate. Understand the concept of acid strength and its relation to dissociation. Neutralization reactions. Define neutralization as the reaction between an acid and a base, typically forming salt and water. Predict the products of neutralization reactions. Electrochemistry overview. Electrochemistry is the study of the relationship between electricity and chemical reactions. It involves redox reactions, where electron transfer occurs, and is applied in various technologies and natural processes. Batteries, electrochemical devices that convert chemical energy into electrical energy. Examples include primary, non-rechargeable, and secondary, rechargeable batteries. The process involves oxidation and reduction reactions at the electrodes. Corrosion, the degradation of materials, usually metals, due to electrochemical reactions with their environment. It involves oxidation of the metal and reduction of an oxidant, often oxygen or water. Methods to control corrosion include coatings, cathodic protection, and inhibitors. Aluminum production. Aluminum is produced by the electrolysis of alumina, Al2O3, dissolved in molten cryolite. This process, known as the Hall-Hill process, requires significant energy input. The process involves the oxidation of the aluminum ions at the anode and the reduction of aluminum ions at the cathode. Fuel cells. Electrochemical devices that convert the chemical energy of a fuel, like hydrogen, and an oxidant, like oxygen, into electricity. They offer high efficiency and produce only water as a byproduct. Fuel cells consist of an electrolyte, an anode, and a cathode. Physiological processes. Electrochemical reactions are essential for various biological processes. Examples include nerve impulses, muscle contractions, and the transport of ions across cell membranes. Redox reactions are crucial in metabolic pathways. Electroplating, a process that uses electrochemistry to deposit a thin layer of a metal onto the surface of another material. It is used to improve the appearance, corrosion resistance, and other properties of the coated object. The process involves using the metal ions in the solution as the anode and the object to be plated as the cathode. Electrocatalysis, the use of electrochemistry to catalyze chemical reactions. It involves using an electrode material to speed up a chemical reaction. It is utilized in various applications such as fuel cells, electrolysis, and organic synthesis. Balancing redox reactions overview. Balancing redox reactions involves ensuring that the number of atoms and the total charge are equal on both sides of a chemical equation. Equalizing electrons gained and lost. Multiply the half reactions by appropriate coefficients to make the number of electrons lost in oxidation equal to the number of electrons gained in reduction. Adding appropriate states indicate the physical states, solid, liquid, gas, aqueous, of all reactants and products. This provides a complete and accurate representation of the reaction conditions. Balanced electrochemical reactions combine the balanced half reactions to create a balanced overall redox reaction. The final equation should have both atoms and charges balanced. Galvanic cells overview. Galvanic cells are electrochemical cells that generate electrical energy from spontaneous redox reactions. They convert chemical energy into electrical energy, utilizing the flow of electrons through an external circuit. Electrode composition, copper, zinc, typically involves two different metals. Voltage prediction, predicting the potential difference. Current prediction, predicting the flow of charge. Cell voltage calculation. Nernst equation, calculating cell potential under non-standard conditions. Oxidation states overview. Oxidation states represent the hypothetical charge an atom would have if all bonds were completely ionic. Oxidation state of an element. The oxidation state of an element in its elemental form is 0, for example, O2, Na. Oxidation state of a monatomic ion. The oxidation state of a monatomic ion equals its charge, for example, Na plus is +1, Cl is -1. Oxidation state of oxygen. Oxygen usually has an oxidation state of -2, except in peroxides, for example, H2O2, where it is -1, and when bonded to fluorine, for example, OF2. Oxidation state of hydrogen. Hydrogen usually has an oxidation state of +1 when bonded to nonmetals and -1 when bonded to metals, hydrides. Oxidation state of fluorine. Fluorine always has an oxidation state of -1 in its compounds. Sum of oxidation states in neutral compounds. The sum of the oxidation states in a neutral compound is 0. Sum of oxidation states in polyatomic ions. The sum of the oxidation states in a polyatomic ion equals the charge of the ion. Stoichiometry and chemical reactions overview. Stoichiometry is the study of the quantitative relationships between reactants and products in chemical reactions. It uses balanced chemical equations to calculate the amounts of reactants needed or products formed in a reaction. Molecular and empirical formula. Molecular formula represents the exact number of atoms of each element in a molecule. Empirical formula represents the simplest whole number ratio of atoms in a compound. Determining formulas involves understanding molar mass and elemental composition. Solutions and concentrations. Molarity, molality, molarity, M, is defined as moles of solute per liter of solution. Molality, M, is defined as moles of solute per kilogram of solvent. Concentration calculations are essential for stoichiometry involving solutions. Limiting reagents. A limiting reagent is the reactant that is completely consumed in a chemical reaction, determining the amount of product formed. Identifying the limiting reagent is crucial for predicting the theoretical yield of a reaction. Percent yields. Percent yield is the ratio of the actual yield, experimentally obtained, to the theoretical yield, calculated, expressed as a percentage. It measures the efficiency of a chemical reaction. Balancing chemical reactions. Balancing chemical equations ensures that the number of atoms for each element is the same on both sides of the equation, adhering to the law of conservation of mass. Balancing is a fundamental skill for stoichiometric calculations. Deposition on electrodes. Electrochemical reactions involve the transfer of electrons, leading to the deposition of substances on electrodes. Stoichiometry is used to calculate the mass of a substance deposited or the amount of electricity required. Electrode potentials and calculations overview. Electrode potentials are fundamental in electrochemistry, describing the tendency of a substance to gain or lose electrons, which is crucial for understanding and calculating voltage, current, and charge in electrochemical cells. Voltage, definition and measurement. Voltage, electric potential difference, is the driving force that causes electric current to flow. Measured in volts, V. Electrochemical cells, describes the potential difference between two electrodes in a cell. Determined by the difference in electrode potentials of the half cells. Standard electrode potentials, the voltage associated with a half cell under standard conditions, 298 K, 1 atmosphere, 1 M. Used to calculate the cell potential, EMF, under standard conditions. Current and charge calculations. Current, a rate of flow of electric charge. Measured in amperes, A, where 1 equals 1 coulomb per second. Charge, the fundamental property of matter that causes it to experience a force when near other charged matter. Measured in coulombs, C. Relationship between current, charge, and time, charge, Q, equals current, I, x time, TQ equals IT Faraday's constant. Definition, the charge carried by 1 mole of electrons. Value, approximately 96,485 coulombs per mole, C per mole. Use in calculations. Used to relate the amount of charge passed in an electrochemical reaction to the number of moles of electrons transferred. Q equals NF, where N is the number of moles of electrons and F is Faraday's constant. Can calculate the mass of a substance deposited or produced during electrolysis using Faraday's constant and the stoichiometry of the reaction. Redox reactions overview. Redox reactions, or oxidation-reduction reactions, involve the transfer of electrons between chemical species. These reactions are fundamental in various chemical and electrochemical processes, and they are defined by changes in oxidation states of the reacting species. Oxidizing agent, a substance that causes oxidation by accepting electrons. The oxidizing agent itself is reduced in the process. Reducing agent, substance that causes reduction by donating electrons. The reducing agent itself is oxidized in the process. Electron transfer, the actual movement of electrons from one species to another in a redox reaction. This transfer is the driving force behind the chemical change. Electrochemical reactions, redox reactions that involve the generation of electricity or the use of electricity to drive a chemical reaction. These reactions occur in electrochemical cells. Cell potential, the measure of the potential difference between two electrodes in an electrochemical cell, indicates the driving force for the redox reaction to occur. Half reactions represent the oxidation or reduction process separately. They are combined to balance the overall redox reaction. Galvanic cells. A galvanic cell, also known as a voltaic cell, is an electrochemical device that converts chemical energy into electrical energy through spontaneous redox reactions. These cells consist of two half cells, each containing an electrode immersed in an electrolyte solution. Key components and concepts include anode, the electrode where oxidation occurs. It is the source of electrons and is often assigned a negative charge in a galvanic cell. Cathode, the electrode where reduction occurs. It accepts electrons from the anode and is often assigned a positive charge. Salt bridge, a U-shaped tube containing an electrolyte solution that connects the two half cells. It allows ions to flow between the half cells to maintain electrical neutrality, preventing the buildup of charge. External circuit, wires that connect the anode and cathode, allowing electrons to flow from the anode to the cathode, generating an electric current. Cell notation, a shorthand representation of the galvanic cell, typically written as anode solution vertical bar cathode solution, cathode. Equations and calculations. The overall reaction in a galvanic cell is a spontaneous redox reaction. This can be broken down into two half reactions, oxidation half reaction at the anode, reduction half reaction at the cathode. The cell potential represents the voltage difference between the two electrodes and indicates the driving force of the reaction. It can be calculated using the standard reduction potentials of the half cells. The standard cell potential is measured under standard conditions, 1 N concentration for solutions, 1 atmosphere pressure for gases, and 25 degrees Celsius. A positive cell potential indicates a spontaneous reaction and a functional galvanic cell.